तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This will be lecture number 6 on mechanical measurements. Towards the end of the last lecture, we were talking about nonlinear fit, and in particular we talked about a polynomial fit. So what I intend to do in the present lecture is shown in the slide. Polynomial fit, I will take an example of a quadratic fit, and before taking the example through Excel, I will actually work out a few steps on the board so that we understand what we are talking about. I will actually derive or show how the normal equations are written, and then I will follow it up with the example 6, which talks about the quadratic fit for a particular data set. Having discussed that, we will consider the general nonlinear fit in some detail. As I mentioned in the previous lecture, it will not be very detailed, it will only give a sketchy description of how to go about doing a nonlinear fit. And I will just discuss in brief the so-called method of steepest descent, which is one of the optimization methods which can be used for nonlinear regression. Time permitting, I will give a brief introduction to experiment design, and of course it will be taken up in more detail in the subsequent lecture. So just to recapitulate what we have done, we were talking about a polynomial fit which means that I have a nonlinear relationship between a variable y and the variable x. I am just assuming one variable here for the sake of simplicity. So I am thinking in terms of y being given as a polynomial of x. A particularly simple example would be a quadratic which will be given by a naught plus a1 x plus a2 x squared. The three parameters which characterizes this fit or characterize the fit are these three parameters: a naught, a1 and a2. So the expression which I have here, y equal to p of x, will be used when it comes to the application of this model as yi equal to p of xi. That means I can elaborate it and write it as yi equal to a naught plus a1 xi plus a2 xi squared. So the problem consists of determining the constants a naught, a1 and a2 by using the method of least squares, because that is common for all regression models. So let us just elaborate on this a little more. So what I will do is, I will try to minimize the sum of squares, which is given by sigma I equal to 1 to n y minus yi whole square. This will be data comma I, and this will be yi, which is the fit. This is the fit and this is the data. And all I have to do is to substitute for yi the expression from the previous page. You see here we have yi equal to a naught plus a1 xi plus a2 xi squared. I just have to substitute here into this one, and we will say this will be a naught plus a1 xi plus a2 xi squared. So, the procedure is very similar to what we did when we were doing the linear regression model. If you remember, we were taking the partial derivative with respect to each parameter in succession and then writing the appropriate equation which makes the partial derivative 0. For example, we had in the case of linear regression we had two such equations. In this case we will have three equations which are required for finding out the three parameters a naught, a1 and a2. So, these are obtained by requiring, suppose I call this quantity as some capital S. So, I requirement is dou S by dou a naught is equal to dou S by dou a1 equal to dou S by dou a2 equal to 0. That is the requirement for the minimization of this. That means that this minimization requires these steps here. So, if we do that, you can immediately see that instead of two normal equations, we are going to get three normal equations. And let us just see what the normal equations are by writing down the expressions for dou S by dou a naught or any one of them. For example, I can take dou S by dou a2. This will be sigma I equal to 1 to n two into ydi minus a naught plus a1 xi plus a2 xi squared multiplied by I am going to now differentiate with respect to a2 because I have taken differentiation with respect to a2 here, that will give you xi squared. If you want, you can put the whole thing in a flower bracket because the entire thing here is dependent on xi, of course with a negative sign. So, that negative sign can be introduced here, so no problem. So, you see that now if I rewrite in a simple slightly different form as is clear to us from our earlier treatment, you will have a naught sigma xi squared from here to here, the product of these two plus a1 sigma xi cube plus a2 sigma xi to the power of 4, this is equal to sigma ydi multiplied by xi squared. We will refer to this as equation number 1. It is very clear, if you remember what we did earlier when we had only two equations, this equation was absent actually in that case. And you will also notice that the summation involves 4th power of xi, then the cube of the xi and the square of the xi. This is the equation number 1 in this case. So, by recapitulating what we did earlier, we can simply write the next two equations, and I would like the student to find out how to get them. So, the next equation will be a naught sigma xi plus A1 sigma xi squared plus A2 sigma xi cube is equal to sigma ydi xi. I can call this as equation number 2. You will notice that A2 is multiplied by, instead of xi to the power of 4, it is xi cube. So, 1 power less than this. This is also 1 power less, and this is also 1 power less. So, this is xi squared. It becomes xi in the case of the second equation. So, this is xi squared and this xi in the equation. So, similarly, we can write down the third normal equation, which is obtained as A naught into sigma 1, or this is equal to n times A naught plus A1 sigma xi plus A2 sigma xi squared is equal to sigma yi. Actually, this equation has a very simple meaning, that actually y bar x bar is again a point on the regression curve. So, x bar y bar is again a point lying on the regression curve, which is a quadratic in this particular case. So, we have 3 equations and 3 parameters which are unknown, and we can easily solve for these by using Cramer's rule, or by successive elimination we can do that one, solve by any suitable method. Of course, this is how one would get the answer, by actually working out the problem. However, in Excel, as we indicated in the last lecture, there is an option. When you go to the chart option, in the option, one of the options is going to be, in fact, we had a large number of options. In fact, to recapitulate, we can have a linear, polynomial. So, when I say polynomial, I can specify the highest power or the degree of the polynomial. You can also have exponential, moving average, and so on. So, one just has to use this option, and whatever calculation procedure I showed is automatically performed by the Excel itself, and I am going to get the answer straight away. So, in order to appreciate this, what I will do is, I will go back to the slide which depicts some of these. So, let me look at the particular slide which gives some information about it. So, I have just recapitulated whatever I wrote on the board. So, the polynomial fit is easily done using analytical method by formulating the problem as an optimization problem, deriving the 3 normal equations, and we can obtain a solution which we worked out on the board. Or I can use Excel, which has a built-in routine for this case, and what I am going to do is, in the next 2 or 3 slides, I am going to show how this can be easily done by Excel. So, let me take a typical example. The XY data set is shown in the form of a table, and we expect that there is a quadratic relation between y and x. We are expected to obtain the fit by the least squares method and discuss the goodness of the fit. And if you remember in the last lecture, when we were talking about nonlinear fit, we said that the appropriate parameter which will tell us about the goodness of the fit is the index of correlation. In the case of linear fit, we call it the correlation coefficient, and we are able to derive it by looking at the slopes of two regression lines and looking at how close they are to each other by taking the ratio of these slopes. In the case of nonlinear fit, such a simple interpretation is not possible. So instead of that, what we are doing is to compare the error or the spread in the data with respect to the regression line or regression curve and compare it with the spread in the y with respect to its own mean. And in fact, we come out with the index of correlation as the appropriate parameter. So that is what I am going to show in this case. In fact, the index of correlation automatically comes out as an output from the Excel calculation sheet. So let us look at the example in the Excel sheet. So I have just taken the Excel sheet and then I have copied the appropriate numbers onto the PowerPoint so that we can see the numbers more clearly and more legibly. So the data is given with x ranging from 0.2 to 3.5 here, and the y is the data which goes from 2.55 to about 35.37. And already it has been made clear to us that we can expect a quadratic relationship between x shown in the first column and the y shown in the second column. So let us look at the sketch before or the plot before we go on to the goodness of the fit. So what I have done is I have used the Excel program to calculate the appropriate or choose the proper trend line, and in this case the trend line was a polynomial. So when we choose the polynomial as a trend line, it will show like this. Polynomial, POLY stands for polynomial. So this is automatically showing that we have chosen a polynomial. And I have given the title here quadratic fit to data. That means I have chosen a polynomial with degree equal to 2. Actually what one can do is, he can, if no information has been given to you, or if you do not know what is the proper thing which we should use, we can try out different fits using the trend line options available in the Excel program, and then find out which is the best by your standard. You look at it and then decide which is the best and then choose that one. So in this case, because the information was given that we are expecting a quadratic fit or a polynomial of degree 2, we have directly chosen the polynomial. So the fit is given by the formula 2.2318 x squared, 1.5132x plus 2.1807. This is A0, this is A1, and this is A2. I have written in the reverse order. And you see that the coefficients of all the terms A0, A1, A2 are roughly of the same order. That means all the terms are equally important in this particular example. This quantity, this as well as this. And if you remember, the maximum value of x is 5, therefore 3.5, and x squared will correspond to about a little more than 10. Therefore, this will be a dominant term for a large value of x. And for small value of x, of course, the other two terms are in fact the first term is going to be dominant, and then slowly the second term becomes important, and the third term is going to be most important when you go to very large values of x along the x axis. I have also plotted the error bars on this. Before we do that, I will look at how good the fit is, and then come back to that sketch. So I have compared the data and the fit by actually evaluating the values of the fit values at the corresponding values of x given in the table, and I have made a table which gives you the x values in the first row. The second row consists of the data which has been given to us, and of course I have rounded off the y values calculated by the fit again to 2 decimal points, so that we have consistent comparison between the two data and the fit. And you can see that if you take a look at any of them, the difference between these two, 2.57, 2.55. Here 8.29, 8.07, and if you go here 35.4, 34.8, the spread or the difference between these two values, the one shown in green data values, one shown in brown color, these differences are small, indicating that the fit must be a good fit. And in fact, it is further amplified by looking at the R squared value. As I indicated, the R squared value also comes out from the Excel program. Directly it gives you the index of correlation, and that is given by 0.998, which is a value which is very close to unity, and therefore obviously it means that the fit is sufficiently good for our purposes. And in fact, I have also calculated the index of correlation myself by using the definition given earlier, and the index of correlation is, in fact, it is nothing but the square root of the R squared value, and the square root of a number which is less than 1 will always be more than the other. So this is slightly bigger. So we are getting almost 0.999 index of correlation. The other one was 0.998. And in fact, I can also calculate the standard error. And how do I calculate the standard error? I am going to calculate the difference. If I go back to the previous slide, I am going to take the difference between these two quantities, the green and the brown values, square them and add for all the points which are given here, and I am going to divide it by n minus the degrees of the total degrees of freedom, which is n minus 3, because there are 3 parameters which have been determined by using the normal equations. Therefore, I am going to divide it by, not number here is about 13, instead of 13 I am going to use 13 minus 3, 10. Therefore, that is going to give me the expected error or the standard error, and it comes to 1.0246. I can round it off to 1.03, for example. And what I have done is, I have in the plot, I have shown the plus or minus that value as the appropriate error bar for the values. That means that the values of the fit value represents the data within that. If the errors were within that region, which is shown by these error bars, it still will give you comparable results. That means within that limit we can use the fit as a representation of the data. So this is something about the quadratic or the polynomial fit. And now let us look at the general nonlinear fit problem. The difficulty with respect to the general nonlinear fit problem is, it may be represented by an equation which is difficult to handle. Of course, any fit will have certain parameters which is going to characterize that, and in fact in a few minutes I will show you some of the nonlinear fits which cannot be handled by actually deriving the normal equations and so on. So only under such conditions we need to go about solving using some method which optimizes or which minimizes the sum of the squares of the error, and that is what I mean by an optimization problem. Let me just go to the board and try to look at some of these. So the general nonlinear problem, so let me just take general nonlinear fit. Which is an expression which cannot be written in a form which resembles the quadratic or cubic and so on. It is not a polynomial. So it cannot be a polynomial, because if it is a polynomial there is no need to worry about the general procedure. Let me just give one or two simple examples. One will be, let us say one is y equal to a e to the power of bx plus cx plus d. This is an exponential term, this is a linear term, it is a combination of exponential and linear, and if I write down the normal equations it will be difficult to do that. Okay? So this is one case which is not amenable to the simple method. a second expression. For example, maybe I can put one more constant here, I can put a d here or a c here. So, you see that in this case, let me just change the, I will introduce one or two more constants. For example, so this is these two expressions are what we can classify as general nonlinear fit, and it is difficult to use the method which was used in the case of polynomials. Just to develop the method, let us just look at what we are trying to do. So, the general problem is I have got the sum of squares as usual I equal to 1 to whatever n number of data. So, y data minus y, I will say fit I whole square. So, we want to minimize this, and this is a general nonlinear function with p parameters. Here p may be 2, 3, 4, whatever the number. So, what I have to do is I have to find out the values. For example, if p is equal to 3, that means that I may have A, B, C. Choose such that or choose such that S is the smallest. So, before we proceed, let me just look at this quantity here. Because it is a sum of squares, it is always positive. Okay. So, suppose I make a sketch of S. For example, I can you remember that I have A, B and C. I have got A, B and C. So, if I use values, let us say A naught, B naught, C naught arbitrarily, I am just choosing A naught, B naught, C naught as 3 different constants which describes the fit, and therefore, we will call it the fit parameter. I will call it fit parameter set. That means, I am looking at 3 values A, B and C at the same time, and what is its effect on the value of S. Okay. So, I can say that if I have A naught, B naught, C naught as the 3 values, then it will give you some S superscript 0. Okay. This may or may not be the minimum. So, we will say may or may not be the minimum. How do we verify whether it is or it is not a minimum? All I have to do is to find out the partial derivatives and compare with 0. If each one of them is 0, then of course, we can say that S has become a minimum and therefore, this is the minimum value. So, we have to evaluate the partial derivative with respect to A, B and C at these assumed values. So, I will just say, I will put a bar here and say at A naught, Actually, I have to say A naught, B naught, C naught. I think I will change the, that becomes subscript. I have to put the, this will be A naught, B naught, C naught, and similarly here. So, I am evaluating the derivatives with respect to A, with respect to B, and with respect to C. If each is 0 independently, then it is a minimum, then a minimum. That means I have to verify at each stage what is the value of the partial derivatives. So, let us look at these partial derivatives slightly more closely and look at a Taylor expansion. For example, y is a function of A, B and C. I am talking about the parameter. Instead of y, I should use the value of s here. So, s is a function of A, B, C. Of course, it is a function. S is after adding all the terms, I am getting this. Therefore, now S has a dependence on A, B and C values. For example, if it is A naught, B naught, C naught, S is equal to some f of A naught, B naught, C naught. So, I can find out what is the slope of this or the gradient of this quantity. This will contain 3 components which are nothing but dou S by dou A, dou S by dou B, dou S by dou C, and I will in fact write this along this direction of A. So, I will say unit vector along the direction here and here. So, I will just say this is the gradient, this is the gradient. So, the requirement for a minimum is achieved when equal to 0. That is what we are looking for. We will also look at this gradient slightly in more detail. Now, what does the gradient indicate? It indicates the partial derivative with respect to the 3 parameters. So, I am talking about the parameter space. Maybe I can even make a simple sketch to show that. So, which I will do in the next sheet. So, I have, suppose I plot A here, B here and C. Each ABC combination is going to give one value of S, and let us put that as the value here. Now, the gradient is giving me the slope of the variation of S with respect to the 3 values A, B and C. So, it will be a line which may be passing through these 2 points. For example, it is a line. This is tangential to the surface which is characterized by S of A, B, C. Okay. So, let me just write it slightly bigger. So, I have the point which is S, and the gradient is a vector which gives the direction in which it is varying by the largest amount, and therefore, I can show the direction like this. Of course, it can be either going in the direction along which it is going to change, and the slope is given like this. Okay. The slope of this line is the magnitude of the gradient, the slope equal to magnitude of gradient. So, what I can do is I can find out what is the direction in which it is. We know that the gradient is the direction in which the maximum amount of change will take place, and what I will do is I will go in the direction of reducing value of s. So, I will go, we move along the reducing value of s, or in the direction opposite the gradient. So, this let me explain by showing what is being done. We have already calculated the 3 components. Of course, if there is a problem with more number of parameters, there will be more number of these, and in fact, I can calculate the sum of the squares of these 3 and take the square root. This is actually the magnitude. From this magnitude, I can also obtain the direction cosines of the components or we can construct unit vectors, a unit vector given by the following. So, dou s by dou a divided by its magnitude, I will say magnitude is delta s. Okay. Similarly, and so we have the 3 components of the unit vector which is parallel to the gradient vector. So, if I take the step, I know that s is not a minimum because this magnitude should be 0. Because it is not 0, I know that it is not the maximum. Therefore, I want to go to the next point by taking a step which is proportional to the component multiplied by certain small value which I can choose and multiplied with a negative number, because I want to go in the direction of decreasing gradient. Therefore, let us look at that one. So, what I will do is I start from a naught, b naught, c naught. I may next take the step such that I will have a1 is equal to a naught minus some small quantity, I will call it delta, which is chosen by us multiplied by the component in the direction of unit vector component along a naught. This will be given by a naught minus delta the dou s by dou a evaluated at a naught, b naught, c naught divided by magnitude of course, this is also evaluated at the same point. So, what do I expect if I do that? So, if I do that, I am going to expect the following. Of course, I have to write such expressions. I have to write such expressions for the others also. So, a1 Similarly, B1, here I will have B0 minus delta times same delta. Delta is the same for the 3 increments, because they have to be parallel to that vector. You should not multiply by 3 different numbers. The delta must be the same for the 3, because I am going to move parallel to those quantities. Okay? So, if I do that, what I should expect is, if I were to plot, let us just look at one dimensional case, just to see what is happening. So, this is the point where the value was S0. I took a step in the direction of decreasing S0, and therefore, next I will come here. I have just exaggerated. And next step I do exactly at the same thing. This will be S1, it will go like this. So, it is approaching the minimum value. So, what I am doing is, I am going in the direction exactly opposite to the gradient vector, and therefore, it is moving along the steepest or the fastest change as far as the value of S is concerned, and therefore, this is called the steepest descent method. I have indicated only for one parameter. This can be done for any number of parameters, and what you are doing is, you are moving towards like this. You are taking small steps each time and moving towards smaller and smaller values of S, and of course, you stop somewhere when it does not make sense to do any more. For example, if S has become, does not change by more than some epsilon chosen by us, then stop. Of course, in this method, if you take too large a step, it may actually miss, and it may start giving trouble as you reach the minimum point. Therefore, initially we may have to do a little bit of experimentation, find out the suitable value of delta. Initially we may take slightly larger delta, but once we close in on the minimum value, then we should start reducing the value of delta and obtaining it. So, the whole point of this discussion has been to just indicate that the general optimization or general regression using a nonlinear model is possible by using a simple technique of minimizing by using an optimization technique like the steepest descent method. It may or may not work always, and therefore, there are better methods and so on, but of course, we just want to understand briefly what we are trying to do. So, in case you do not want to spend too much time and effort in doing this, you remember even the linear regression and the polynomial, exponential and so on, we are using Excel, which has all the built-in programs. We can also use other programs which have built-in routine for doing nonlinear regression. For example, there is a program called Axum, which can do this. Whatever I explained in the previous slides, whatever I explained using the board and wrote down the procedure for steepest descent and so on, these are built-in programs available in Axum, and therefore, you can use Axum for doing that. Or a program like sigma plot can be used, where you can specify any complicated expression for the regression model, and then it will be able to do that. There is also a program called NLREG or nonlinear regression, which is available as a free download from the net. One can go to the net and freely download this particular program and use it for doing nonlinear regression. So, at this juncture, we will assume that we have learnt enough about regression, and of course, one learns regression by actually collecting data, making plots, fitting curves and so on, which is an experience one has to learn by actually doing. Whatever we have given is only a sort of an introduction to the area of regression. There is a lot more to it, and the amount of time we have in this particular course is limited, and therefore we have to stop there. So what we will do is now, having understood something about measurement principles, something about errors and their characterization, we talked about the statistical properties of the errors, and then we proposed what is called the least square principle, and then based on that we have been able to do the regression analysis, either linear, quadratic, nonlinear and so on. So this is the background which is required by any experimental worker. Anybody who wants to do experiments and wants to present data in a proper form, acceptable to other people who are working in the same field or who are going to be using your data, you must know all these things and use it carefully. So with this background, let us look at what other things we have to do in conducting experiments, and I am just going to give a brief introduction to the area of the experimental design, and in this next lecture I am going to cover it in more detail. So what is the goal of experiment? In fact, we have already touched upon it in the very first lecture. We talked about the need for goal of experiments, and I am just recapitulating here, probably in a little more detail. So experiments, as you can see from the slide, it helps us, experiments help us in understanding the behavior of a mechanical system. I have put the mechanical system in brackets because only we are interested in mechanical system in this particular course. It is equally applicable to any area of work in which you may be doing your experiment. So mechanical system is only one subset of all the possible areas in which one could do the experiment. What do we do in an experiment is to collect the data by systematic variation. I am going to introduce some words which are going to occur again and again in design of experiments. One of them is the influence factors, influencing factors. So there is a fancy name for the independent variable. You remember y equal to f of x, x is varied independently, x is a factor. So that means that the outcome of the experiment, which is the measured value y, is influenced by the value of the factor x or the variable x. So we call it a factor. In an experiment, for example, temperature, pressure, humidity, so many different things may play a role, and each one of them becomes a factor. Okay? This is just a terminology. The data collected systematically by varying the factors in a proper systematic fashion over the range of values which we have already decided. What is it going to do? It is going to help us to quantitatively describe the underlying phenomenon, if there is one phenomena, or maybe several phenomena are taking place at the same time. Maybe they are influencing each other. How to get the information about these underlying principles or phenomena, that is our goal. So what we are going to do is to do several experiments, and how do we decide some of these issues? For that we have to look at what are the things we are doing. For example, in a manufacturing process, if you are trying to make some machine part, for example, you will be interested in the machine component and its quality and find out what are all the factors which are going to influence that. For example, in a typical process, you may be using a machine to either modify the shape or the surface finish or whatever it is. And in this process, I am going to use some parameters, like for example, the speed at which I am going to run the machine, the depth of cut, for example. So each one of these becomes a factor. The depth of cut, the speed at which the machine is running, so this becomes a factor, these become the factors, and the end product, the shape of the product or the size of the product or the nature of the surface of the product depends on these factors. So what I would be interested in from the point of view of manufacturing would be to look at what is the best suitable values for all these parameters or the factors, such that I am able to satisfy some requirement, like the surface finish has to be within certain limits. So it may be a single quantity that is being estimated. If you look at the slide, it is a single quantity that is going to be estimated, That means that I am interested only in the one particular process in which the outcome is one particular thing I am looking for, and I want to find out how to choose the parameters or the factors such that I am going to get that. That is one kind of experiment, which is of course very important in mechanical engineering. Or I may be doing an experiment in fluid mechanics where I am not interested in one particular small bit of information. I want to do the general, get a general understanding of what is happening. So I may be measuring one quantity which depends on a certain other quantity, like we were talking about regression. Regression is finding out what is the linking relationship between two things, the one which is measured or one factor which is kept constant or varied in a systematic fashion, and the outcome of that experiment will be some quantity which is of interest to us. For example, in the case of a fluid flow problem, I may be interested in the pressure drop in a certain length of pipe, for example, and it will be determined by various factors including the velocity of the flow, the diameter of the pipe, and so on. I would like to know what is the underlying relationship. I am not looking for one particular information, I am looking for a global information about the variation with respect to the various parameters. So the experiments you are going to do, the number of experiments you are going to do, and the type of experiments you have to do will depend on some of these important things, whether you are interested in only one parameter, one quantity which you want to measure or optimize, or you want to get the trend. Then if you are looking at the second kind of experiment where you want to find the trend, you would like to ask the question whether the trend is linear or non-linear. So depending on the variation, if it is linear, we can do very few experiments and get the information. If it is non-linear, the relationship is not one to one, one straight line variation. Therefore, we would like to know how undulating the curve is, how curved is the relationship, how non-linear is the relationship. The more the non-linearity, the more number of data we have to collect to represent that non-linearity in greater detail. Of course, this will become clear as we go forward in the next lecture. Then we would like to answer also or ask the question, how different are the coefficients, influence coefficients. That means what if you have a relationship or the trend between two variables or more than two variables, we would like to ask what is the importance of each one of these. This can be important even in the case of a manufacturing problem. For example, the case I gave, the surface finish may be dependent on two parameters or two factors, that is the speed of the machine and the depth of cut. It may be more influenced by one of them and less influenced by the other. So we would like to make the experiment and from the experiment find out which is the more or which is the factor which has got higher influence. It also may be there may be an interaction between these factors. If the speed of the machine is very high and the depth of cut is very small, or depth of cut is very high and the speed of machine is low, it may lead to different types of interaction. So the two factors may even interact, and the outcome of the experiment may be a thing which depends on both of them simultaneously. Therefore, to answer all these questions, we would like to do the following. What are the different things available? I will just like to mention them, and in the next lecture we are going to take a greater, deeper look into this. For example, in the case of fluid flow problems, we may do a dimensional analysis and find out whether it can give us some information regarding what we are looking for. So can we identify, for example, the dimensionless groups that influence the quantity or quantities being measured? That is the question we would like to ask, and we would like to find out, is it possible? And then of course, the most importantly, we would like to find out how many experiments we must perform to get the information we are looking for. This leads to the general problem of design of experiments, and this involves several steps. And what I am going to do is I am going to address both the kind of problems. You have one process and you want to optimize the process, find out what are the factor values you must choose by simple experiments, or you may want to get the trend between various factors and the quantity of interest to us, and we would like to see how to design such experiment. Both the questions will be taken up, and possibly it is going to take 2 more lectures. So the next and the subsequent lectures 7 and 8 are going to deal with these things, and that will bring us to the close at that time to the first module of this set of lectures on mechanical measurement. Thank you. you.